Afshin, last week you had done that, right?
Yes, I started, teacher.
Please start it, and we can start. Okay. So in this week, we will talk about the. You remember in the first week we made some introduction to well logging, right? Now this week we will go some more details. I will give some more details regarding on the well logging to you. Okay. Some basics, but very crucial things, which will be very beneficial in your future career as well. If some of you will go to the field, and these tricks will be very beneficial. Okay, so I will give you these tricks regarding on mallogging, and then we will talk about the gamma ray log, spontaneous potential log, and caliper logs. Okay, so I will start to the course, but first of all, what we have to do, we have to remember some basic information. What are these basic informations? What are these basic informations? The hydrocarbon geology, first of all. The hydrocarbon geology, as you remember from your previous courses, or you joined to the workshop that we had done last month, oil and gas are formed in a place that has a temperature window between 120 Fahrenheit to 350 Fahrenheit. Okay, between 120 Fahrenheit to 350 Fahrenheit. It needs a zone which has very low permeability and form in this section. And after a while, sourced by some natural events like earthquakes or fault creation or forming faults, etc. This hydrocarbon content, okay, this hydrocarbon content finds a way and migrates through to the upper parts until it finds a caprock, right? Until it finds a caprock. When it finds the caprock, it stays, and it started to be formed according to its density, okay, with the elevation. It starts to form like that and stays in there. It cannot pass the caprock part, right? So this is the first information that we remember. Okay, the second one, hydrocarbon traps. As you know, we have many types of hydrocarbon traps, like anticlines. This is the most, around 70% of all reserves are in this type, right? Anticlines. Faults, okay, a fault can cut the formation, and what happens, it creates a kind of caprock, and for oil and gas forms in the beneath of this. Salt diapirs, as you can see, salt is also an impermeable zone, so it creates a kind of caprock, natural caprock in here. Some unconformity trap, okay, as you can see in the picture. Reef type of trap and other stratigraphic, it's very complicated traps. Okay, so all types can be combined, and we call it combination traps. Okay, so you know it's not just one type of traps we can find in the nature. It's lots of types of traps occurs in the formation. Okay, so because of that, first of all, we have to have an idea regarding on what type of trap we have, what is the structure, what type of rocks we are dealing with. Okay, we have to describe all of these. Okay, so as you can see, for example, all of these in another picture. So anticline traps, pinch outs can be happen like this, unconformity can be fault type, salt dome, as I mentioned. Okay, so what happens when you drill your well onshore or offshore? Okay, so you have to deal with all these formations. Okay, so following your drilling operation, during drilling or following your drilling operation, what happens? The first thing that we have to do, we have to understand the lithology. Okay, the lithology. For example, I found a reserve. Okay, for example, let's say here somewhere. Okay, I found a reserve in here. but I don't know which lithology it has. Okay, it's Jurassic, Triassic, or Cretaceous. Okay, or Permian, much more lower. So what type of lithology I have? What is the time? What is the geological time of it? Okay, so I have to describe all of these. So the hydrocarbon content. What will be the hydrocarbon amount inside? It's oil or gas. If it is oil, what type of oil? Okay. So what about the shale structures around that? Okay, or anhydrite formations around that which are impermeable. Okay. So I have to have an idea regarding on all these informations. And we are using logs to gather all these informations. Okay, this is the easiest way of doing this. All right. So because of that, we are using well logging. It can be during the drilling or it can be after the drilling. But the basic materials, well log tools, and the basic strategy to gather this information is well logging. Okay. So well logging types, you are seeing here the general well logging types, the borehole, seismic, okay, the first of all. So when we are creating model, actually I put these slides in the eye of a reservoir engineer, okay. So a reservoir engineer want to build a static or dynamic model, okay. So some type of logs are used in static model, some type of logs are used in dynamic model. So if it is a borehole seismic log, you use it in static mode. If you have a mud log data when you are doing your during the drilling or just after the drilling, you can get some mud log data. Okay, so you use it in static model. You have your core data. You had done some core analysis or you had done some analysis on your well cuttings, drilling cuttings. Okay. So you have to use this one in interpretation of the models and uncertainty, and it can be used in both static and dynamic models. Okay. So while you are drilling your well, you do some open hole logs. What you mean by open hole logs? Before the casing, before cementing your casing, putting your casing inside and cementing your casing, you already drilled your well and it's open hole. Okay, it's directly open to the formation. Okay, your well is directly contact with the formation. Okay, so at this position you can get some logs like resistivity log, nuclear log, acoustic log, and some others. Okay, but these are the basics. Okay, so when you gather this information and do your casing after that, okay, and cement it, so you already got your information regarding on your formation. Okay, so because of that, you are very advantageous. Why? You made your casing, you cemented it, and after finishing your drilling, the first thing that you will do, what's that? You have to clean your well, you make your acidizing, and then you have to perforate it. So when you will make your perforation, you will have a clear idea because you had done your open hole logs with previously. Okay, so you have clear information before you got it before making your casing, before performing your casing operation, cementing operation also. So when you got these open hole logs, okay, so you make some corrections like invasion, layering, deviation. This type of corrections need to be done. Okay. Because why? Because in the closed wellbore area, it will be invaded by some mud, right? Your drilling mud. So you have to eliminate it to get the real info regarding on your reservoir, right? So these invasion factors need to be considered. Layering information, okay. So you have to compare your results with neighbor wells because the layering can show some differences compared with your neighbor wells, or a new structure can be involved to the game. Okay, so you have to check and correct all of these. Double check with your neighbor wells. The deviation, this is a very good one because I know some operations, especially in geothermal wells in Turkey, they are doing this. I know some of these wells, they are thinking that they are drilling vertically, but 30, 40 degrees up to 50 degrees, they can be deviated. Okay, so you have to describe the degree of the deviation. So these logs are very essential to describe that as well. Okay, and then following your drilling operation, if you are still if you leave your well open hole, you did not put any casing, or you did not do any cementing operation, you can take wireline logging as well. Okay, so while drilling you can do it with special tools, and while after drilling with wireline you can do the same logging operations. Okay, so in terms of reservoir monitoring, you will get case toll logs. Okay, what do you mean by case toll logs? You put your casing, you have done your cementing operation, you finalized it. Okay, your drilling already finalized. Okay, you have a completed well sketch. So you can still get some logs. Okay, why we are doing this? We are doing this because we need to understand the situation of your casing, the situation of your casing, the situation of your cement, the situation of your cement bonding. Okay, the bonding of your cement has been done successfully, or if you couldn't do that, you can have some leaks. Okay, inside your well from the formation. So this is very tricky and dangerous for the future of your well. So because of that, you have to understand, you have to be sure that your well logging that your drilling and casing operations, cementing operations are successful. Okay, so what type of logs we are taking? Nuclear production logs, mainly these two, and some other special logs which are taken from one company to another. It can change, but some other logs we can say special logs. Okay, another one. So you use these case toll logs, by the way, in interpretation models and uncertainty, and put it to your dynamic model. Okay, directly to your dynamic model. So in terms of reservoir monitoring, again, your field studies, what you mean by your field studies? You made an exploration well, so you have your neighbor wells, right? In the same area. So if you already know the information, so you have to use these field studies and adapt that to your dynamic model, because you already drilled some wells in that field. Okay, so in this case you have to involve these field studies too. Okay, so now let's start to describe some very crucial well logging types. Okay,
Teacher, I have a question.
please.
So what's the difference between static model and dynamic model?
Okay, so in your static model, you assume that your fluids are not moving. Okay, you assume that your fluids are not moving. If this is valid for your reservoir, if you are making a wellbore modeling, so it's valid in your wellbore as well. Okay, you assume that your fluids are not moving. Okay, in dynamic model, you assume that you have a flow. Okay, basically you have a flow in your wellbore, in your reservoir, you have a flow. Okay, if I have a flow, I have to use different equations. If I assume that I have a static model, I use different equations. For example, let me talk about this. For example, when you you started in the future, when you start in a company, you will get some reports. Okay, in these reports, you will see static pressure and dynamic pressure, static temperature and dynamic temperature values. Okay, so same thing, static pressure and temperature means that your well is closed. Okay, your well is closed, your well is not flowing, and waited at least 12 hours. Okay, 12 hours. Some companies accepting that 6 hours is enough, but 12 hours. You waited 12 hours as in a closed position for your wells, and then measure your temperature and pressure values. Okay, so this recorded as static pressure and temperature. Okay, static pressure and temperature. What is the benefit of this? For example, let's talk about the static pressure and temperature. The effects of the convolution, the effects of the convection becomes limited. What happens? The dominated force for heat transfer becomes the effects of the conduction. Okay, so what happens when the flowing stops? Your fluids inside your wellbore, for example, will be much more contact. What with the formation, with the lithology. So it will get the temperature. It will be balanced. The temperature and pressure will be balanced with your hydrostatical pressures and the temperature of that lithology. Okay, by time. So because of that, your static pressure and temperature will be totally different compared with the dynamic one. Totally different. Your dynamic in your dynamic pressure and temperature, it will be much more related. It will much more describe. Will be much more close to your reservoir pressure and temperature compared with the static one. Okay, so you have to describe these very well. These are crucial. If you use, for example, in your dynamic, if you are making a dynamic model and use static pressure data, temperature data, it will not give you the real result. Never. So because of this, it's very important.
Okay, I got it.
Is that clear?
Yes, clear.
Okay. So let's go on. So I will focus on 5 different logs. Okay, so most of them it will be covered. So first of all, caliper logs. Caliper logs are used to measure the borehole size. What we said? We said open hole logs, right? We said open hole logs. So when you are making your open hole log, of course this your drilling bit, okay, it's drilling, but it's not drilling as a circle, right? In some parts it will have some rock parts, so it will be very it will have an unconformity inside your well. Okay, so because of that, you have to use your caliper logs and describe the borehole sizes in each feet, in each elevation. Okay, this is very crucial because in some parts even it can be larger than the bit size. It can be when it is directing, for example, when it goes direction change, it can be in some parts lower than the bit size. Okay, so because of that, you have to measure the borehole size, and we are using caliper logs for this one. I will mention in detail a little bit more in the end of the presentation about caliper logs. So the other one is lithology logs. Lithology logs are used to differentiate sands. Okay, so just keep these in your mind. We will discuss in 5-10 minutes. Differentiate sands, the type of the sands. Okay, lithology logs. And this is a sandstone formation or not. Okay, this is very crucial. In lithology logs, we are getting this. Porosity logs. Of course, from the name you understand that it describes the porosity and the fluid types. Okay, porosity and the fluid types. Velocity logs, it relates your well to your seismic data. Okay, it relates your well to your seismic data. Velocity logs. Okay. Resistivity logs, I mentioned a little bit about this one. What it was doing, it was sending electrical signals to the formation and getting back the signals, and according to this reflection, it was calculating what is the material in your formation, what type of combinations in the rock. It gives an idea regarding on that, and it helps you to understand. It includes oil or gas. Okay, oil or gas or any hydrocarbon content. Okay, so it used to identify the hydrocarbon zones. Okay, so let's describe the borehole size. As you can see in the picture, borehole can be like this. Okay, borehole can be like this. It's not straight. It's not an homogeneous part, so it can be heterogeneous structure like this with lots of unconformity. So because of that, you have to understand the sizes of each part. Okay, each elevation, the sizes need to be recorded. Okay. What we said borehole size is set by the drilling bit, but it is influenced by change in the stress state. What's the stress state we mentioned in here? For example, if you are dealing with shale reservoir, sorry, not talking about reservoir. If you are talking, for example, let's say this is shale, and this is hydrocarbon zone sandstone, right? So the stress UCS factor, when we talk about the perforation step of the workshop, the UCS factor in here is totally different compared with the sandstone because it's very tight, and the strength of the rock is too much, right, compared with the sandstone. So because of that, the action of the drilling bit in this part will be totally different compared with this one. Okay. So what happens, for example, as you can see here, what happened? This is a leak formation compared with the shale, right? So your drilling bit size like this normally. See, your drilling bit size like this. But what happens in here? Because of the stress that is applied from the formation, okay, so your drilling bit has moved around, right? Has moved around. So when it moved around, because it wants to drill, right? When it moves around, it creates something like this compared with this one. This is a straight one, already straight, yeah, almost straight, right? So because of that, when you compare this one with the upper formation, it has too much difference. So when you do your caliper rock, what you do, you get the information in which part the lithology is harder, the strength is higher, in which part it's not. Okay. So the change in the stress state sourced by the borehole breakout, induced fracturing, fractures can be involved to the game as well, and the creep of salt. Salt formations are very very impermeable formations and very hard to drill, for example. So because of that, the creep of salt can be understood from the borehole logging, right? Chemical reactions, swelling clays in shales. As you already know, shales include clays inside, right? Clays has a capacity, it has a capacity to bond water inside, okay? Water inside. So what happens? A swelling effect is happening. So, of course, this definitely changed the borehole size because of the reaction of the bit and the interaction of your bit with your formation. Okay. And the dissolution of salt, we said that creep of salt. Okay, salt formation, salt dome we have, and I am drilling the salt dome. But with the chemical reactions happening with your mud, for example, or with extra pressure created and temperature, so there can be some dissolution of the salt. Okay, dissolution of the salt. So what happens when dissolution of this? Let's say this is salt formation. When dissolution happens, some part of this borehole will go. Okay, will involve to the mud, and you will take it to the surface, right? Some part of it. So because of that, your borehole size will change as well. So in terms of drilling process, this spiral borehole and bit marks can be another reason. The spiral borehole, as I mentioned, your bit starts because of the hardness of the formation. Your bit starts to drill inside parts. Okay, inside parts. Because of that, your borehole size increase, right? And the bit marks, of course, from one bit to another, this operation success can change. For if you put one bit, for example, it can create something like this. If you put another bit, it can create much more bigger borehole in the same formation. Okay, so bit, the type of the bit and the materials used in the bit will be another factor. In next year, I will have some a book regarding on this, the material related to the material science. Okay, and the types of bits are very crucial in this type of operations, the materials used inside the bit. Okay, so let's continue. So we already mentioned the capillary logs, right? Let's make some summation. So what do they measure? The size and shape of a recently drilled hole. Okay, we understand this part. How do they work? They have some mechanical arms which records the hole size, hydraulic systems with calibrated potentiometers. Now, it has some mechanical arms, as you can see from here. These arms can be two arms. Here actually a kind of demonstration. See, there is one more arm in here, like this. One more arm in here, this showed just one arm. This can be 2-armed, 4-armed, or 6-armed. Up to 6-armed, it can be used. What happens? You start to measure from the lowest part of your well, okay, the deepest part of your well. You start to move your caliper through to the upper part in a certain speed, okay? You move it. When you are moving it, all these calipers, the size of the calipers change, right? According to your, it contacted your wellbore, your borehole, and when it is contacting, when it's coming to the upper part, all the sizes change according to your borehole, right? All the size change to the upper. So it records that, it records this change, and according to that, it says that the diameter at 100 to 1,220 feet, the diameter is, for example, 35 centimeters or 55 centimeters. Okay, so it gives you, with the elevation, it gives you a direct measurement of your borehole size. So how are they used? The hole size used to correct other logs, because you made, for example, you made some gamma ray logs or spontaneous potential logs that we will use here in this week. So when you do these logs, these are not measuring your borehole size. Okay, this is just sending the signal to your formation and getting back the signal, right? So this is not measuring your borehole size. So when you measure your borehole size, you can correct these values. By using these values, you can correct your other logs. Okay. Hole volume for amount of cement. This is a very good point. What happens? You put your casing and you cement your well. Okay. But in some parts, what happens? Think that you put a casing in here, right? I have a casing in here. I put my casing and cemented it. So what happens? The amount which stays in the formation part outside of my casing, okay, formation part, the volume will change, okay. So you have to describe what type of what is the volume of the cement that you use to bond your formation to your casing, right? What's the amount of cement? What's the volume of cement? So this is very crucial, because when you are making logging, also you have to correct this as well, because here the cement amount is very low when you compare it with this one, right? Think that I am coming as a casing. This is a casing, okay? So the volume is always changing. My cement volume always changing, right? Is that clear? This part is clear?
Yes, yes.
Okay, very good. So the volume is changing. So because of that, I have to understand what is the volume of cement that I use, because I will make my corrections in other logs, okay, in future logs. So because of that, this is crucial as well. The lithologic information, washout indicative of formation properties. The lithological information, it also gives you, because what happens, according to your borehole size, it is also an indication of the strength of your lithology. Okay, so if your borehole size becomes bigger, it means that you have a strength from your formation, and your bit becomes it becomes harder for your bit to drill, right? When it becomes bigger. So because of that, you can understand what type of lithology you have. Okay, this is a kind of preliminary information, but this is useful. So what type of lithology you have, you can get easily by using your caliper logs. And stress field from the borehole breakout. This is already mentioned. The stress, the amount of the stress that your drill bit deal can be understood easily. So lithology logs. When we mentioned previously gamma ray and spontaneous potential log types we mentioned. So the basic logging actually is gamma ray. Okay, this is the earliest invented logging type. It uses a kind of scintillation detector that measures the natural radiation from the formation. Okay, so there are some radioactive materials, radioactive rocks in nature, and all your rock types include some of these in different percentages. Okay, so and we know this one. For example, what is the average radioactive material involved in sandstone or carbonate? We know it already. Okay, we know the limitations. So because of that, what you can say when you make your reading from your gamma ray, so you can understand that it's sand or it's shale. Okay, this is crucial. So because of that, it is one of the most used lithology logs, the gamma ray one, and spontaneous potential is also used to make a cross check on this one. This is also important. So it makes a measurement by depth of the potential difference between the voltage in the wellbore as a function of depth and electrode on the surface. Okay, so you have an electrode on the surface. You are in a certain depth, and you are checking the voltage, the electrical voltage of that depth, and the electrical and use the electrode on the surface and make your corrections regarding on that, and you got your information related to your formation. We will mention in details now. So, for example, you see a gamma ray log here. This is what happens. It describes its sand, the sand parts, as you can see. What happens? Your gamma ray log reflections change directly, right? So when it's close to the 100, you say that it's 90 to 100, 95, 96. You say that this is shale formation. Okay, 98. You say that this is shale formation. Okay. When it shows some signal differences up to a lower level, 40s, for example, 30, 40, these levels, 50 even, you can say, yes, it's sandstone. I am in the sandstone formation. You can see the signal differences directly, right? You can understand it clearly. So, an easy way to understand this one, the deflections to the right shows you when you got your logging information. The deflections to the right gives you the shale, okay? The deflections to the left side gives you the sand, okay? So this is the easy one. All right. So we are going to porosity logs after this. Lithology finished. Now we are going to porosity logs. The density porosity and neutron porosity, two different log types we have in here used commonly. So again, in the density porosity log, we have a scintillation detector again, okay? And like a gamma ray, it also measures the radiation coming from the formation, okay? In the neutron porosity, the measurement versus depth of the potential difference between the voltage in the wellbore as a function of depth and electron on the surface. Same with the spontaneous potential log, right? So use the same idea, but now we have a specialty. We are enabled to measure the gas, oil, or water content too. Okay, so what happens when you compare your density and neutron logs? Okay, these are going in a certain way, right? See the lines? It's going in a certain way. So I can understand that this is a shale formation. Okay. both of them going in a certain way, I understand that this is a shale formation. So one of them started to move to the right side, the other one moved to the left side. Okay, so cross sectional it goes. Okay, when I combine the elevations, okay, when I mesh the elevations, I see that there is a cross sectional passing, one to the right, one to the left side. So I can say that, okay, see, this is a very clear cross-sectional path, right? Very clear cross-sectional path. So I can say that there is a hydrocarbon in here, okay? And then it comes back, and my density porosity shows totally different way, okay? So I will say that here, what it comes, density porosity, from density porosity, it comes to the shale again, okay? So my shale started again, right? But it doesn't reflect to neutron porosity, but I understand from density porosity, I came to the shale formation. And then my density porosity comes back through to the hydrocarbon content level again, okay? Still, I cannot understand that too much from the neutron porosity, but the density show me differently, definitely, okay? So I see that there is a gas in here, okay? And then it shows a peak, a sudden peak like this. You can see the peak. There is a peak like this. So what is this one? What this can be? Any idea?
We have gas again.
Okay, what is the name of it? We mentioned this. What is the name of it? If I see a sudden peak in here, I have a sudden peak in here, and then it come back. What is this? No idea? Very easy one. Very easy one. Upper part in the upper part is what? Gas. Lower part, let's say oil. So what is that peak? My gas oil contact. GOC, gas oil contact part, okay, GOC. So it's an indication of GOC, okay. Still my hydrocarbon is continue. It is an indication of my gas oil contact, okay. So, and then come back again and continues to recording, okay. And then what happens? A sudden one sudden peak more, and then one more peak, okay, two different peaks I show. So somewhere here I have a contact with what?
Water.
I have a contact, what?
Oil-water contact.
Oil water. So I somewhere here I have a water contact, okay. I can understand. I have a water contact. It gives, it starts to give peaks and come back, right? So I have another contact in here, and it can be water, definitely, okay. Somewhere here, not definitely it says it's certain depth, but somewhere here. So it's a kind of transition zone. This is actually better can be understandable between gas and oil. Okay, it shows a peak. Okay, just one peak. But if it is with oil and water, according to the density difference, what happens? It shows, because these are immiscible, and there will be a transition zone between your oil and water content, right? So because of that, you are seeing these transitional zone changes here, okay? So somewhere in here is a transition zone, and after that part, your water starts. So you can understand these type of things, okay? All right. So in here, neutron, I use neutron to differentiate what? The shale structure and my hydrocarbon content, okay. In density in density porosity like this. In neutron porosity, what I understand, sorry, I'm mixing that one. In neutron porosity, I understand that this is shale or hydrocarbon content. In your density porosity, you understand what is the hydrocarbon content in there, okay. You differentiate shale with hydrocarbon content first of all, and then you understand what type of hydrocarbon content you have, okay. Hydrocarbon or water. All right. So basically, So herein
Yeah, I have a
deflections,
question.
please.
In the place where we have gas, in neutron porosity logs, we have peak, yes?
In neutron, yeah, yes, directly.
So why we don't have peak in second place that we have gas and later oil and water?
So you say that this, okay, we have a peak in the upper part, and why we don't have a peak in the lower part, okay? This is the question, right?
Yes, yes.
Okay, so this differentiates, this is not differentiating your neutron porosity, not differentiating the hydrocarbon content. It differentiates you are in the shale structure or another structure, okay? You are in the shale structure or another structure. Herein, the density porosity directly measures your fluids. This is related to fluid. This related to getting the porosity of your lithology. Okay, lithology gets the porosity from the lithology, gets the porosity from the liquids. Density gets from the liquids. Another one gets it from the lithology. So because of that, this differentiate. This is a high porosity zone or low porosity zone. Okay, the red one. So it just gives you the information like this. My shale formation, which has very low porosity, is ended in here, and the higher porosity levels started. Okay. So what happens here? For example, here there is one more shale, right? One more shale, but it didn't differentiate. So what it gives you, it is not as sensitive as it is, this measurement. You can see this is a tiny shale section I have, but it didn't differentiate it too much, right? I didn't understand from the neutron. So because of that, I have to use my neutron porosity log with density porosity log together, always. Okay, I have to measure both of them. So when a company comes to you, service company, which logs I will take? Okay, which logs I will take? First of all, you will use your gamma ray. Take gamma ray directly. Use your density and neutron porosity. Okay, you have to select this density and neutron porosity, because one of them just gives you it's shale or not. It's shale or a formation which has more porosity. The other gives you it is shale or another formation, and what is the liquid inside that, what is the fluid inside that. Okay, what type of fluid it is. Clear?
So can we say neutron porosity log is kind of lithological log?
Yes.
Because it shows where we have shale or where we have
This
sandstone.
one.
Yes, yes.
Yes. You repeat again, okay?
So can we say neutron logs is kind of lithology logs, because it shows us where we have shale or where we have sandstone.
Neutron logs gives you the porosity value. Okay, porosity. So it is a porosity log. It is in the classification of porosity log directly. Okay, because it gives you the porosity.
Measurement types difference.
Yes. What data I am getting. Okay, what data I am getting. So because of that, your neutron logs gives you directly your porosity. Because of that, you have to involve it in porosity logs type. Okay, it's porosity log.
Okay.
All right.
Okay, thank you.
So your lithology logs, when you see the lithology logs, you will understand gamma ray and spontaneous potential. That's all. Okay. When it comes to porosity logs, density and neutron porosity log, two types of logs, which gives you the porosity, because I am getting the porosity as a output value. Okay. So because of that, in terms of your output value, we are evaluating it. Okay. So because the neutron has to be included in the porosity part. All right.
Okay, okay.
Okay. So A trick in here, the deflections to the left, means it's more porous, okay? The deflections to the right is less porous, like shale, right? Dashed red light, dashed red left of solid black line gives you the shale. Dash red right of solid black gives you gas sand. Dash red over solid black is wet sand or oil sand. Okay, this is the definitions and easy way to differentiate the signals. Okay, so record this one. This will be beneficial in your future. Okay, when you are in field, this will be very beneficial. So what about the sonic velocity logs? We said velocity logs, okay. So sonic velocity logs is type of velocity log. It uses acoustic energy which is emitted by a transmitter. Sonic signals it sends, okay. This sonic signals travels through the formation and fluids inside formations and fluid, and then what happens when it contact with the fluid and the formation? Some part of this sonic signals revert back to the wellbore, and it got read by the receivers. Okay. So the log displays the interval transit time in microsecond per feet as the inverse of velocity. Okay, so because of that, we call this one sonic velocity logs. So let's check what's happening. Your rock formation, your tool in here. You have the receiver 1, receiver 2. Okay, so you send your signal from the upper part. This is 2-3 feet, not more than that. So you have your transmitter. Your transmitter sent the signal through to the rock formation, and this signal has been taken by the receiver 1 and receiver 2. Okay, so of course there is a difference between these two paths, right? There is a interval difference, certain interval difference, which are already known. According to this difference, what happens, and the time you know the time as well, time change as well, because the signal comes first with this R1, second to the R2, right? Because of that, you know your time change, you record and you calculate your time change, delta t, and these interval transit times recording as the inverse of the velocity. Okay, you know the feet, how many feet it is, and you know the delaying time of the signal reaching to the receivers, and you record these interval transit times. And according to this, you make your logging. You make your logging readings. Okay. So we will go into details of sonic velocity in next weeks. I will pass to the resistivity logs. Okay, so we said that caliper logs, we said that lithology logs, we said gamma ray and spontaneous potential as lithology logs. We said porosity logs, neutron and density logs included to this one, because we were getting it in terms of getting the output values. Okay, we are classifying into getting output values. So density and neutron log, and sonic velocity logs, fourth, and the resistivity log. And the resistivity log we will mention. Okay, resistivity log, it sends electrical signals, we said. Here you will see some definitions like deep resistivity, medium, and shallow resistivity. This refers to how far into the formation the resistivity is reading. Okay, if it is 4 feet, you set deep. Okay, deep resistivity measurement. 2 feet, medium resistivity. I mean, if it is a few inch length, the signal is sent through to the formation in few inches. So you set that is shallow resistivity. Okay, shallow resistivity. For example, in some parts that you are thinking, you want to understand the effect of your mud cake and the invasion zone, okay, the levels of your invasion zone and the measurements of your invasion zone. You can use the shallow resistivity, okay, or you believe that for example, you used low weight mud in your drilling, low weight mud you use, so you are sure that your invasion zone is very limited, so you can go to shallow resistivity as well, okay. So these are the definitions that we are using for resistivity logs. So the deep resistivity, if you get high values in deep resistivity log, okay, so it gives you the idea regarding on the hydrocarbons and low porosity parts, okay, gives you the hydrocarbons and low porosity parts, okay. But I am not, you see, I am not describing this in porosity logs. I am calling it the resistivity log, right? Because it gives me another ideas regarding on the hydrocarbon content, shale, wet sand as well. What type of lithology I have. It gives idea what type of what is the porosity level. It gives an idea again. But I am putting it in a different manner, like resistivity log, okay. So if I get low values in the deep resistivity, what happens? I understand that I have shale and wet sand, okay. I have shale and wet sand. The separation between resistivities means the formation fluid is different from the drilling fluid. The formation is permeable to the drilling fluid, okay. If you have some separations between the resistivity values of these three, okay, so you understand that fluid is different from the drilling fluid. So it is a certain level that compares your fluid your formation fluid with your drilling fluid, okay. If it is same with your drilling fluid, okay, then what happens? For example, formation fluid similar to drilling fluid set. So you see in all of them, you don't see too much difference. Because why? Because for example, in the shallow one, what happens? It gives you the idea of the very close area of your wellbore, and it is dirty with your drilling mud, right? When you go to the medium one, so it still can have some dirt sourced by your drilling mud, but not too much like shallow one. And when it comes to the deep one, you already in your reservoir part, right? So if there is no difference between your very little difference between your close wellbore area and the deeper part, so your formation fluid is similar to your drilling fluid, right? Similar parameters it has, density, for example, very close, so you can understand what is it. So if it is, if you see a difference like that, so you understand that your formation fluid is different from your drilling fluid, okay? So differences, there is a difference or not, no difference, okay? According to that, you can understand, all right? Any question in here?
No question.
Okay, let's go. So now, let's combine all of them, okay? Let's combine all of them. So I have my caliper log, I have my gamma ray log, okay? I have my resistivities, I have my neutron and density log. Okay, this is a real case, by the way. Okay. So we will assume that this well was drilled with an oil-based mud. Why this is important? Oil-based mud or water-based mud we use. Why this is important? Any idea? Because when you describe your hydrocarbon content in your closed wellbore area, If you use the oil-based mud, your oil content will be involved to the game, so you have to make your corrections. Because of that, if you are used an oil-based mud, if you are doing if you use the service company to perform your logging operation, you always certify that this is an oil-based mud or water-based mud used. Okay, so their results you will include that the drilling has been done by an oil-based mud, and when they are making their calculations, they will consider it. They have to consider it in the corrections part, and they have to correct their values. Okay, so step 1, the lithology. Okay, the lithology. So using the gamma ray log, we define where is the shale or there is no shale. Okay, so the deflections far from the left are sands. Okay, the deflections far to the left are sands. So what happens? What I see in here, mostly sand formations, right? So intermediate deflections to the left are silts. For example, I see something in here. This is not shale. This is not shale, but I have some reflection in here, so I call it silts, or some more. If you see some evaporates, okay, silts or evaporates. If I see something compared with the normal behavior, something strange like this, through to the right side, so I can describe it as there is a silt structure or evaporates. Okay, if it goes to 90 to 100 degree, so I can say it's shale. Okay, there is no there's zero permeability almost, so it's shale directly. Okay, so this is the first definition. Okay, for example, here in the upper part, it's shale. It showed this actually take the maximum value as in the mid the range problem, I think. So the maximum, when it reached to the maximum value, it considers shale. Okay, this part it considers siltstone, and you know the sandstone already. Yeah, is the yellow ones. But the shale, it considers this one as shale actually. This is actually, if you are in 50 or 60, this has to be siltstone actually. That's something wrongly written in here. So it's like that. Okay, when you reach to 90 to 100, you can consider it as shale. Okay, this is what we can say. Tiny shale structures, maybe tiny shale structures can be tiny shale, but when we were doing this, we already got it as siltstone. Okay, so we understand the idea. So the porosity log crossovers, where is the neutron porosity? To the right of the density porosity. So let's check. When we go to the neutron and the density porosity, we can see some differences in here. Okay. Why it called it shale? Because they compared it with the porosity logs. Okay. So your gamma ray, if your gamma ray gives a certain value in here, up to 50, 60, right, something like that. But when I go to the porosity logs, I can see directly it is shale. Okay, it's directly shale, and this structure, as you can see from the density, it's directly shale. Okay, that's the reason. So as you can see, when I go to the right side from the density log, I said it's shale. This is directly showing shale, by the way. Now I understand. Okay, when I come to the lower parts, okay, so my density is lowered, and this is going into certain level. So what I understand here, where is the neutron porosity? To the right of the density porosity. So when your neutron porosity, okay, the red one, passes through to the right side of your density porosity, you understand that this is a sandstone formation. Okay, note this one. This is a crucial one. When your neutron porosity passes through to the right side of your density porosity, you call it sandstone formation. Okay. See, slightly different and certain level. Not, I am not talking about. Well, so what happened? Your density porosity passes in the lower part. Your density porosity passes to neutron porosity to the right side. Then you call it, it's an impermeable zone called siltstone, right here. Siltstone in here. All right. So it shows, okay, again, it can be understanding here, this shale formation again, okay? When you compare it with your density log, I understand that this is shale. In the gamma ray, it gives a lower value, okay? But always I have to match it with other logs. This is so very crucial. So when I match this one with the density log, I can understand that it's directly shale, okay? I am in the shale level, right? So your gamma ray gives a little bit lower value, but when I match it with the density, directly share. All right. So this is the step 2. First step: compare your lithology log. You have an idea. Okay. So you make a cross check. What you will do? You will go to your porosity logs. You will make your cross check. Okay. Is that true? Is that real shale or real siltstone or sandstone? Check with your porosity logs and combine both of them. Okay. So the third, what it says, says to you, herein it shows that you have a gas content in it. Okay, you have a gas content in it. Okay, you have a sandstone we already described, and you have a gas content in it. Okay, so where is the resistivity logs? So my resistivity logs are here, right? Where do the resistivity logs give the different values? I have to check. Where my resistivity logs give the different values in this part, right? So these are all same, these same. So in this part it gives the different values. Okay. So this indicates where your fluids in the rock differ from the drilling fluid, right? So your drilling fluid, it differentiates your drilling fluid with your actual fluids in your reservoir. So in this zone. So what it gives me, what it indicates me, herein I don't have a potential to produce. I don't have a potential to produce. Here I have a C, for example. I have a sandstone in here, right? This is sandstone formation as well. But there is no hydrocarbonate. I cannot produce from here. I cannot produce from here as well, but I can produce from here. There is a hydrocarbon contact because I see some differences compared with my hydrocarbons, compared with my drilling mouth. Okay, so there is a hydrocarbon contact in here. This is understood from this one. This gives that it is gas. This gives that it is sandstone formation. Okay. All right. So herein it passes like this, but for example, my neutron log value is much more bigger. To the left side is much more bigger compared with the density. Okay, somewhere here you see, then you are passing through to the oil. Okay, your hydrocarbon composition changes and it comes through to the oil part. So here it shows the few difference, shows you the gas. If this increase, it shows you the oil. Okay, these are very close to each other, so you can say gas. If my neutron is higher to the right side, I will say it is oil hydrocarbon. Okay. Okay. So formation fluid is similar to the drilling fluid. Okay, formation fluid is similar to the drilling fluid. We used an oil-based mud. The two green zones are interpreted to be oil. Okay. The corrections made, and it indicates us the formation fluid, because the formation fluid is similar to the drilling fluid in here. So we used oil-based mud. So because of that, these two green zones are interpreted to be oil. Okay, to be oil. So another thing I would like to mention, the well rock correlation. For example, here you have 4 different wells. Okay, 4 different wells, but structures, the elevations are different in structures, in terms of structures, right? This is the 4 neighbor wells in the same field, but the structures are changing. Okay, so you have to correct all of this, and you have to correct the lithology because of that. Okay, I will mention this one. The well logs gives us the detailed information at the location of the borehole, we said. If there are several wells in an area, we can correlate stratigraphic units between them. All right. The correlation is based on characteristics of the well log responses, like a fingerprint. It's a kind of fingerprint of your wellbore, and it changes from one to another. Okay, the lithology changes from one to another. What we mentioned, I will explain to you. For example, oftenly what we do, we select the datum point. Okay, we say a correlation horizon for this. That's registered to a common depth. Okay, we set that, for example, 1000 meter. I select as a datum point. Okay, so at this behavior, I have to I have a two choice to use. Okay, two philosophies, it says, used in well log correlation. So what are these? The first one is the lithostratigraphy. Okay, you correlate all your lithologic units. You correlate it based on your lithologic units. You call it lithostratigraphy. If you correlate it based on the timelines, so you have to say chronostratigraphy. So what are the difference of these two? Okay, so let's say, for example, here's 4 different wells we got. Okay, the green one shows coastal plains, sandstones and mudstones. The yellow one, shallow marine sandstones. Okay, sandstones. And other one, the lower parts, shows shells, mudstones. Okay, so from one to another it changes, as you can see, because it differentiated. For example, what happened? This formation, for example, here, when it comes to this part, there is a shallow marine sandstone came inside somewhere here, came inside these two, and divided this part to 2 different parts, right? Sorry, to 2 different parts, and this become like this in well C, right? Comes to the upper part. So, for example, in here, this part came to the upper, this part becomes like this, this part is somewhere like this, but from the lower part, another part came to this, right? So this part, for example, in well D becomes lower compared with the well C. So it changes from one well to another directly, okay, the lithology. So when you make it common, when you describe it through to your lithological units, what happens? You get something like this. I have a datum point, and I have to correct through to the lithology. So I have a map like this, okay, in terms of all wells. Okay. So what happens? I demonstrate the real structure, because what happens? I combined all of these, all the structures I combined, and I got the lithological view of all the structure of in each intervals, in each depths in here. Okay. So another one. This is the chronostratigraphy. So according to the chronostratigraphy, I put a datum point according to, for example, the fossil types. Okay, according to the fossil types, they describe the datum point, and according to this, what happens? You have to combine. You combine the same structures in a certain, according to this datum point, in a certain way. You combine, and you got a map like this. Okay, see, this is lithological. This is chronological. Okay, according to the times. Okay, according to the times. Times means here is Jurassic, Triassic, Cretaceous. You know, this type of timing, according to the geological times. Okay, so these two used in the correlation of the logs. Okay. So, does it matter? Does it matter? Yes, it's matter actually. It's not matter to find a field, okay? A difference. There is a hydrocarbon content or not. It doesn't make any difference. But when you are making your estimation of your resource, okay, your estimations of your resource when you are making it, this will be very crucial because the amount will change according to your calculations. And if you use the lithostratigraphy, it will be different. Chronostratigraphy, it will be totally different. So it will change your development plans as well. In the future, your development plans, it will affect in some way, more technical, no worries. In enhanced soil recovery, it will change because of the locations that you described, okay? For example, a guy who worked, a geologist who worked with the lithostratigraphy in most time, when you give some results of chronostratigraphy to him, okay, so he can apply a certain different field development plan, okay, or use a different enhanced soil recovery method, okay. So because of that, it's very crucial. It has to be described, okay. It has to be described what type of correlation, what type of correlation it used, okay. So let's make an overview. Let's make an overview. Properties versus log types. Okay. So I put this. Figure. It will be very useful for all of you. Actually, this has been taken from ExxonMobil. You see the all log types in here, in the upper part, and the properties. Okay, and the properties in here. So if you are talking about the lithology, I think this will be a kind of answer to your previous question. If you are talking about the lithology and mineralogy, okay, see, gamma ray gives you a big idea, okay. Spontaneous potential gives you the big idea. Coarse gives you the big idea, okay. It totally describes it. Sonic density, neutron, resistivity, nuclear magnetic resonance, photoelectric effect gives you a small idea about that, limited idea, we say. You cannot get this by wireline testing, well testing, or deep meters. Okay. So for the porosity, sonic log, density log, neutron log gives you a bigger idea. You said that why we are not including neutron to the lithology, because it gives you much better idea about porosity, right? So porosity, nuclear magnetic NMR gives you a big idea about porosity and cores. Okay. So fluid type, density, neutron, resistivity, wireline testing, of course, well testing, of course, you can get it. Cores, you can get it. Fluid saturation, again, density, neutron, resistivity, NMR, little limited information. Sorry. Limited information, and coarse gives you higher information. Permeability, you can get it from SP log, sonic log, density, neutron, resistivity. You can have a limited idea, but nuclear magnetic resonance, wireline testing, well testing, and coarse gives you a big idea. For example, in your wireline testing and well test results, when you get your pressure and temperature data, what happens? You do your well test interpretation, and according to your well test interpretation, you can get directly your permeability values, right? In a correct way. Stratigraphy, gamma ray spontaneous potential gives little bit, okay, but mostly borehole imaging and core holes. And deep meter, it says it's not used too much. As you can see, it's not used too much. And borehole image and cores mainly gives you the idea. Wireline and testing, well test gives you the downhole pressure. Geophysical properties, sonic and density logs gives you idea about geophysical properties. Gamma ray log and resistivity logs gives you little idea about geophysical properties. So this is a very crucial figure So I wanted to put it in here actually. So let's go some more in details to gamma ray logs, okay? To gamma ray logs. Gamma ray logs use the radioactivity of rocks, which has been used for many years to help to help driving the lithologies. Actually, this is one of the oldest logs. Okay, so actually, natural occurring radioactive materials, they called it norm. Okay, natural occurring radioactive materials includes the elements of uranium, thorium, potassium, all right, radium, and radon, okay, along with the minerals that contain them, okay. So there is usually no fundamental connection between different rock types and measured gamma ray intensity, but there is a strong general correlation between the radioactive isotope content and the mineralogy, okay. So logging tools have been developed to read the gamma rays which emitted by these elements and interpret lithology from the information collected. Okay, so conceptually, what we can say, the simplest tool that we are using is passive gamma ray devices. Okay, these are the simple ones to identify the permeability zones and lithology. Okay. Actually, this is what we can say regarding on the gamma ray logs in the beginning. All right. So a gamma ray log example in here with the colored version you can see here. So Earth formations we said are radioactive due to the presence of naturally occurring radioactive isotopes of uranium, thorium, and potassium. So gamma ray logging measures the natural gamma radiations. Okay. Its application area to identify the permeable zones and lithology, shale volume calculation, and well depth correlation. Okay. So, for example, here you can see the radioactivity of rock types. Okay, as can be seen from this figure, the distributions of radiation levels observed are plotted for numerous rock types. Okay, this is an old actually figure. It described by Russell. It's described by Russell, I think in 1950s, end of 1950s, something like that. So here evaporates, which I called sodium chloride, salt, and anhydrides that I already mentioned, impermeable zones actually, are and coals also typically have low levels. Okay, as you can see here, typically they have low levels. Okay, and you can see in the first two, I think. You can see in the first two, and in other rocks in general, trend toward higher radioactivity with increased shale content is apparent. Okay, when you increase your shale content in the formation, so the radioactivity actually increases. Okay, at the high radioactivity extreme are organic rich shales and potash. It says potassium chloride. Okay, potash means potassium chloride in the lower part you see. Okay, so these plotted values can include beta as well as gamma radioactivity collected with a counter called Geiger counter. Okay, so modern techniques concentrate on the gamma ray detection. Directly, it concentrates on gamma ray detection. It doesn't use the beta. The latest technology tools directly use gamma in here. Okay, so let's pass to another slide. The radioactive isotopes in the rocks. Okay, we said potassium, thorium, uranium, and radium series. Okay. Kilo electron volt gamma ray energy, and the probability of emissions per disintegration is given in here. Okay, so you see some peaks. Okay, some certain level of peaks in the spectrum of these different materials, these different radioactive isotopes. Okay. So the primary radioactive isotope in the rock are potassium-40 and the isotope series associated with the disintegration of uranium and thorium. Okay. So in the figure, you see the equilibrium distribution of energy levels associated with each of these groups. Okay, these spectrums shows the energy levels associated with potassium in the first one, thorium and uranium radium. Okay, so potassium-40, for example, potassium-40 produces a single gamma ray of energy in 1.46 millielectron volt. Okay, and it directly transforms into stable calcium. Okay. On the other hand, when we checked the other ones, for example, in the thorium and uranium as well, it breaks down to form a sequence of radioactive daughter products. Okay, you see in the spectrum, it shows too much peak levels. Okay, so because of that, according to these certain peak levels, when you see these peak levels, you say that this is thorium or this is uranium. Okay, according to the certain gamma ray energy, if you get, for example, in here, I get this type of gamma energy, this amount of gamma energy. In uranium radium, I get this type of gamma energy. So I can understand that this is uranium or radium, not thorium. But if I get something like this, I say it's thorium. Okay. So standard gamma ray tools measure a very broad band of energy, including all the primary peaks, as well as lower energy daughter peaks. Okay. So this is the classification of, for example, the thorium. This spectrum is the classification of thorium. I know it. It's proved. And this is the same thing for uranium and radium. Okay, classification. So, okay, this is the radioactive isotopes in rocks. We said. Let's see. For example, here you see two tables, right? You see two tables. In the left table, it lists some of the common rock types and their typical content of potassium, uranium, and thorium. Potassium is an abundant element, so the radioactive K40 is widely distributed, okay, in all materials. Very in a wide range of it can be seen clearly. So, potassium, feldspars, and micas are common components in igneous and metamorphic rocks. Okay, so immature sandstones can retain an abundance of these components. In addition, what we can say, potassium is a common in clays. Is a common. Okay, so under extreme evaporatic conditions, the silvite, we call potassium chloride, it's called silvite as well, potassium chloride, will be deposited and result in a very high radioactivity levels. So uranium and thorium also, on the other hand, are much less common, very radioactive and much less common. So both uranium and thorium are found in clays by absorption. But we said clays has a tendency to absorb materials and water too much, right? So as a result of this absorption, you can find uranium and thorium in clays as well. Okay, and besides that, you can find it in volcanic ashes and heavy minerals as well. Okay, so according to this radioactive isotope behavior, you define what type of lithology you have. Okay, so gamma ray 2 measures natural radioactivity of the formation from the emission of all of these in the total GR, we call. Total GR, if you see total GR, it includes all potassium, uranium, and thorium results. It's the total combination of all of these. Okay. So GR log is used for well-to-well geological correlation, bed definition, more accurate than the spontaneous potential log. Okay, the second lithological log, remember. Shale volume indicator. This is the most reliable one for shale volume indicator actually. Lithology and mineralogy indicator also. Okay, so the formula here, the gamma ray index formula, when you see your GR log minus your GR minimum value, your GR shale baseline value minus GR minimum value, okay, gives you your gamma ray index. Okay, it's the basic formula that it gives. So we said what happens in here. What happens? There is a radioactive decay. Okay, when you are making your gamma ray logging, as you can see in here, your tool is moving in the upper part. So from your radioactive elements, like normally in a resistivity of what we were doing, we were sending the signal and getting the back signal, right? Here, these radioactive elements are sending the signals directly themselves. Think like that. They are sending the signals directly themselves. So what happens? Your logging tool directly records these signals. Okay, these radioactive signals. So because of that, your GR tool, the recording of your GR tool, when it is moving, is recorded by the elevation, by each elevation. Okay. So here, for example, what you got, the density values, it calculates the density values, okay, indirectly, quantitatively, it calculates the density values for quartz, calcite, dolomite, and other minerals, and it gives you directly by reading these reflections coming from the radioactive material. It gives you the gamma ray results. Okay. Gamma ray readings. Okay. Here I would like to mention a little bit about the photoelectric absorption and the Compton scattering. Actually, this is happening in the process of this gamma ray readings. Actually, photoelectric absorption. When your radioactive photon comes to an atomic particle, okay, if it collides through to the first orbital in the inside, it ejects an electron. Okay, it ejects an electron. This is called photoelectric absorption. Okay, and this electron turns into a photoelectron. Okay. In the Compton scattering, in the outer orbital, the same thing happens. Okay, a scattered gamma ray and the Compton recoil, two different particles go out. Okay. If we are talking about the pair production, what happens? It goes to the inner orbital, collides, the gamma ray collides, and then it participates as electron with the negative loaded, and electron with the positive loaded as well. Okay, so it's a strange thing. Negative loaded electron and positive loaded electron, both of them, as a result of this collision, can reflect from the atomic particle. Okay, so this is a very rare thing. It's very rare. It's pair production, but mostly photoelectric absorption and Compton scattering are most common ways. Okay, and the gamma ray source is based on this one actually. Okay, the gamma energy loses. And main categories in the process of gamma energy loss due to the collisions with other atomic particles. Okay. I described this actually in the multiphase flow metering issue of the workshop, the week 3, the same thing, because that tool also working in the same mechanism, and gamma ray tool also working in this mechanism too. Okay. All right. So okay, here there are some newer wells. as you can see. I wanted to put this one because it's a good example. There are some wells and gamma ray and resistivity readings of these wells here, as you can see. For example, you can see the similar behavior in different depths, okay? And the depths match actually. Depths matched according to a datum in here. See, for example, this behavior, you got it from in a different depth. And this behavior, this is actually same lithology. See, same lithology. You got the same behavior in different wells in different sections. Okay, so according to your gamma ray and resistivity results, what happening? You directly describe by combining all of these, all your neighbor wells. Okay, for example, I remember that Rumeila field in Basra had more than 1,500 wells. So when you make logs to these 1,500 wells, okay, so you directly get the lithological behavior of your whole field. The whole field behavior comes to you. You map your field according to your intervals and depths, right? So in which, for example, the change of the depth of this formation can be got for all these 1,500 wells. And you make correlations between you correlate one well to another, and you estimate what type of lithology between these wells, right? So it gives you in the total mapping, it will be very beneficial for you. Petra, I think Petra is doing this very good, in a very good way. Okay, so some type of things can be done. Can be some ultimate things, some tricky things. What type of things these are? For example, in the mud, drilling mud, we can use barit. Okay, so barit is a very heavy material. Okay, your mud becomes very heavy if you add barit to it. So, for example, here the density window of your gamma ray is between this level. Okay, but when it comes to your so your lithology window is here. You see the region of photoelectric effect. So your low barit and mud thickness, okay, when it increased, it will give you some results between these two. Okay, when your barit becomes higher, level of barit becomes higher, so your clot will come to the up like this with the higher barit. Okay, so your gamma ray counts will show lots of differentiations compared with the amount of the barit used in your drilling, during your drilling, inside your drilling mud. So because of that, you have to understand this carefully, and when you are making the corrections in the software, you have to describe the mud type. If it is a barit mud like this, you have to describe it, and the corrections has been done by the software, so you have to include it. Okay. All right, these are the things that I will say regarding on the gamma ray log. Now let's talk a little bit about the spontaneous potential log. Okay, sorry. Let's talk a little bit about spontaneous potential log. Very good. So now I will explain. Actually, I will examine how to explain the spontaneous potential, how it is created in the formation and borehole. Okay, and how spontaneous potential log is measured. Actually, okay. So the SP log, actually a kind of SP curve. It creates a SP curve, spontaneous potential curve, and this curve is a continuous recording with the depth of electrical potential difference between a movable electrode in the borehole and the surface electrode. Okay. Adjacent to the shales, SP readings usually define a straight line known as the shale baseline. And the next to the permeable formations, permeable formations, the curve departs from the shale baseline in thick permeable beds. And these excursions reach a constant departure from the shale baseline. Okay, so it defines as sand line. Okay, it defined as sand line. So the deflection may be either to the left side, we mentioned already, or the right side, positive, right? So depending on the relative salinities of the formation water and the malt filter rate as well, this changes. So if the formation water salinity is greater than the malt filtrate salinity, which is the more common case, the deflection will be to the left side. Okay, it will be to the left side. The relevant features of the SP curve are its shape and the size of its departure from the shale baseline. Okay, because of the absolute reading and position of the shale baseline on the log are irrelevant. The SP sensitivity, actually, shale and shale baseline position are selected by the logging engineer for convenience. Okay, so mainly, okay, these two measures natural electrical potentials occurs in the borehole. It separate and understand the porous material. There's a porosity in here or not. It is permeable or not. Okay, it's a permeable sandstone, for example, from intervening shales. Okay, it directly differentiates shales with the porous material and sandstone structures. Okay, so the natural battery is caused when the use of drilling mud with a different salinity from the formation waters causes two solutions to be in contact that have different ion concentrations, it says. Ion diffuse from the more concentrated solution, typically more concentrated solution is formation water, to the more dilute one, like hydrocarbon content or mud. Okay, the ion flow constitutes electrical current which generates a small natural potential measured by SP2 in millivolts. So the definition is given to you, the output value is given to you in millivolts. Okay. So do you remember? Okay, let me talk a little bit about the background of each of you. So you will remember this one from your high school, I think, right? What was the direction of an electrical current? Current is defined as moves in the same direction as positive charge flow, right? So the charge carries the electrons the charge carriers are negative, and the current is in the opposite direction as the electrons, right? The opposite direction as the electrons. So from the negative charge, the electron has a tendency to go to the positive charge, and from the positive charge, the protons has a tendency to go to the negative charge. And this, as a result of this, what happens? The current occurs, right? Okay, the spontaneous potential use this actually. So basically, the spontaneous potential log is used to detect the permeability zones, to detect the boundaries, to detect determine the formation resistivity of water, determine the shale volume in permeable beds, and well-to-well correlation. Okay, I mentioned well-to-well correlation, right? Previously. So the property measures the formation voltage and the passive measurements. Okay, so according to the voltage chains, like this, for example, when it is in a shale, it has a certain reading, and then suddenly changes to the left side. It indicates that the porous permeable bed in here, right? Minus 71 it reads, right? So according to this one, according to the current change, through to the left side in the minus side, so we can describe this permeable porous bed, right? All right, so SP log principles. when you are using spontaneous potential log, your your mud has to be water-based mud. Okay. First one, this one, water-based mud has to be used. Mud formation water salinity difference. Mud formation water salinity difference causes the battery effect. Okay. And the battery effect components, electrochemical components and electrokinetic components, sourced by the delta P. Okay. So in the electrochemical components, there are two parameters. First of them called liquid junction potential, the diffusion, EJ. Okay. The second one is the membrane effect, EM. Okay. For example, shales acts as a membrane always. Okay. So I will describe these two, by the way. This is very crucial. I will describe in details. Okay. Electrokinetic differences usually minor and disregarded in most cases. Some actually the tools, for example, Schellenberger tools is describing this as well, including this to the calculation as well. But in most cases, it's disregarded. Okay. So the origin of spontaneous potential. SP is naturally occurring potential in the borehole, which is sum of first the membrane potential between the shale and the sand. Okay, the membrane potential between shale and the sand. Okay, the liquid junction potential, the red ones. The electrokinetic effect is sometimes observed, but it's rare and rare and short-lived. This part. Okay, as I told you, some tools are very successful to observe this one, the tree, but most of them not. Okay, and it happens very rarely. Okay, so most of them not including this one. Just calculate these two. Okay, so the membrane potential. Okay, so your EC, the total electrical potential, is summation of the membrane potential and liquid junction potential, we say. Okay, so the membrane potential, actually, how we can explain the membrane potential? For example, the structure of clay minerals in shales and the concentration of negative electric charge on clay particle surfaces, okay, give shales a selective permeability to electrically charged ions. Okay, to electrically charged ions. So most shales act as a cationic membranes. Okay, cationic membranes, which are permeable to positively charged ions called cations, and impermeable to negative ions called anions. Okay. So as you can see from the upper part of the figure, here you can see a saline formation water in a sandstone formation and mud in the borehole separated by shale, right? So sodium chloride, which is usually present in both the formation water and the drilling mud, separates into charged ions, sodium and chloride, in solution in water. Okay. So the sodium and chloride ions tend to migrate from a more concentrated to a less concentrated solution. Okay, but because of the intervening shale is a cationic membrane, the impervious to chloride ions, only the sodium ions can migrate. Chloride could not. Okay, so if, as usual, the formation water is more concentrated sodium chloride solution than the mud, there is a net flow of positive ions through to the shale from the sandstone to the borehole. Okay, so this corresponds to a positive electric current in the same direction, which is indicated by the curved arrow in here. You see. Okay, so it's driven by electrical potential or called EMF, electromotive force, EMF. Okay, so across the shale. So because the shale acts as an ion selective membrane, the electric potential is known as the membrane potential. So EM comes directly from the shale actually. Okay. Okay. So what about the liquid junction potential? Let's talk about liquid junction potential. Okay. Actually, at the edge of the invaded zone, okay, at the edge of this invaded zone, okay, you can see at the edge of the invaded zone, where the mud filtrate and the formation water are in direct contact with sodium and chloride ions, okay, these sodium and chloride ions can move freely from one solution to the other because there is a direct contact, right? But chloride ions are smaller and have greater mobility than sodium ions. So what happens? The net diffusion of ions from the more concentrated formation water to the less concentrated malt filtrate includes a greater number of chloride ions than sodium ions. So this is equivalent to the positive current flow in the opposite direction. Yeah, it indicated by the straight arrow, for example, here the straight arrow that you used in A. Okay. So the current flows across the junction between solutions of different salinity is driven by, we called in previously EMF, right? Is this driven by EMF called the liquid junction potential. We call this directly liquid junction potential. So the magnitude of the liquid junction potential is only approximately 1/5 of the membrane potential. Around. Okay, 1/5 of the membrane potential. Okay. So for the liquid junction potential, the formulation is given as can be seen in the slide. So here, AW and AMF, two different parameters, and the ratio of these two is used. The activities of the formation water and the malt filtrate, as I mentioned. Here, when we are calculating the K3, we use the viscosity values. This is actual mobility, not viscosity. These are mobility, because mobility, what is mobility? Mobility is, do you know, do you have any idea about mobility? What's the ratio of two parameters? What are these parameters? Any idea? Mobility. You heard previously? No? No question? No idea about this?
No, teacher.
Okay, mobility is the ratio of permeability and viscosity. Permeability divided by viscosity gives you the mobility. Okay, permeability divided by viscosity gives you the mobility. Okay, so here what happens? Mobility of chloride is a parameter. Mobility of chloride, mobility of sodium. Okay, mobility of chloride minus mobility of sodium divided by mobility of chloride plus mobility of sodium. Okay, the ratio of this one, and this is a 2.3 is a constant in the formula. Ideal gas constant, absolute temperature, and Faraday constant it use, and it calculates the K3. Okay, and then you use this K3 when calculating your liquid junction potential with the activities, with the ratio of the activities of formation water and the mud filtrate. Okay, so you calculate your liquid junction potential there. Okay, so we said liquid junction potential and membrane potential, right? Now let's go to membrane potential again. So the membrane potential, in the membrane potential, you know, it's coming from the shale, we said, right? So the shale here acts as an ion sieve. Okay, acts as an ion sieve. Shale allows the passage of sodium ions, but not chloride ions, as I mentioned. Shales are mixtures of various clay minerals, which are composed of silicium, aluminum, and oxygen. Okay. And the commonest are kaolinite, montmorillonite, and illite clays, right? The silicon and the oxygen atoms are arranged in a tetrahedral structure. You can see in here in tetrahedral structure. Okay. So the sheets have negative charge, which attracts positive ions called cations, such as potassium, sodium, calcium, silicium, and barium. Okay. The membrane potential is based on this mechanism. So, in the membrane potential, the formation water salinity is higher than mud. Formation water salinity is higher than mud salinity. Okay. The shale allows the only sodium ions to move from the formation into the mud by diffusion, not the chloride ions. It's very crucial. The mud becomes more positive than the formation as a result of this. And the net effect is a membrane potential, which is around 5 times larger than the junction one. Okay, liquid junction one. So let's give the formula of this one, the membrane potential. Yeah, the membrane potential is larger than the liquid junction potential since the absolute value of mobilities enters in rather than a difference. That's correct. The magnitude of the liquid junction potential is only about 1/5 of the membrane potential. We already gave this. So herein, the same thing we are using as K4 in here. When I put the K4 for the same parameters, I calculate my membrane potential. What happens? The values, of course, are different in here when we compare. Okay, the values are totally different. So, as you can see, averagely, the membrane potential and liquid junction potential ratios are around 5. Okay. All right. So, the current directions actually indicated the correspond to the more casual case of formation water salinity greater than the multi-filtrate salinity, which produce potential by the permeable bed lower than the potential by shale. Okay, so this corresponds to a deflection to the left on the SP log by the permeable bed. Okay, so SP current flow through 4 different media. Okay, 4 different media. What are these media actually? One of them is the borehole fluid, which has an interaction. The other one is the invaded zone. The other one is formation, uninvaded part of the permeable formation, and the surrounding shales. So the currents of the spontaneous potential uses these different medias, these 4 medias. Okay. All right. So what about the shape? What about the shape of the SP curve? We say, for example, here, as you can see, the slope of the SP curve is actually proportional to the intensity of the SP curves in the borehole at certain depth. Okay, so because the current intensity is highest at the boundaries of the permeable formation, the slope of spontaneous potential curve is at a maximum. Okay. All right. And the inflection point occurs at these bed formations. For example, the figure shows the examples of spontaneous potential curve. Now computed for on the left side. On the left side you see. Okay. On the left side you see RT equals to RS and equals to R mod. Okay. So and in the center one, this one, you see RT equals to RS and it equals around 21 RM. mud resistivity. Okay. So in the first case, the SP curves gives much more shaper definition of the boundaries of permeable beds, and the SP deflections approach to the SSP value. SSP value is static spontaneous potential actually. More closely than in the case where the formation to mud resistivity ratio is 21, equals to 21. Okay, so you can see here two different log values. So you can see one of them, the resistivity values are, you can see much more shaper compared with the other one. Okay, and this one is much more smooth when you compare with this one, right? Much more smooth. So because of that, compression of these two gives you actually it's the description of the shape change of your SP curvature. Okay. All right. So SP anomalies. See, for example, your current, your formations and SP log you can see, and SP currents you can see, as you can see in here. Okay. For example, there are some anomalies occurs. This is crucial actually. When you see something different in your log, you have to describe that. If you couldn't describe it, will create some more problems in future, because in one parameter, if you make your mistake when you're calculating the other based on that parameter, it will create a second mistake too. Okay, so there are some cases which are apparently anomalous in SP responses. So one of them is high resistive formations. Okay, high resistive formations actually between some shales and permeable beds can significantly alter the distribution of the spontaneous potential currents and change the expected shape of the SP curve directly. Okay, the currents, for example, the currents shown in the shale one, in the upper part, in the shale one, toward the permeable bed of P2, okay, are largely confined to the borehole by the high resistivity of the formation, separating the shale 1 and P2, right? The current in the borehole over this interval is constant, right? So for a constant borehole diameter, the SP curve is a straight line inclined to the shale baseline. So the SP curve consists of straight portions adjacent to the high resistivity zones with the change of slope at each more conductive permeable interval. The SP curve is concave, actually concave toward the shale line, right? The SP curve is concave toward the shale line. And opposite of this, every shale bed, the SP curve is convex to the shale line actually. Defining the permeable bed boundaries from the SP log is difficult in the vicinity of high resistive formations. Okay, so one of them is this one. The other one, shale baseline shifts. Okay, for example, in this figure, you can see that the SP log recorded in a series of sandstone called B, D, F, and H, right? Separated by thin shale layers, and the shale sandstones called C, E, and G in here. All right. So the spontaneous, the SSP log, okay, of sandstone B, for example, is minus 42. Okay, it has been given as minus 42 in here, right? Shale C is not a perfect cationic membrane, and the SP curve does not return to the shale baseline defined by shale A, actually. Okay, so a new shale baseline defined by shale E gives SP deflections of plus 44. Okay, in sandstone D, gives this value in sandstone D, and minus 23 millivolt in sandstone F, of course. Okay, so you can see directly understand that there's a tiny shale structure in here actually. So baseline shifts baseline sheets, of course, you have to combine this with another logs as well. You have to understand this one. There's a shale, it can be, you say, but you have to combine with other logs. So baseline shifts also occur when formation waters of different salinities are separated by an impermeable layer, which is not shale. In this case, the spontaneous potential curve shows little or no variation at the level of change in salinity. But the deflections at the upper and lower shale boundaries are different and may even they have different polarities as well. Okay. So normally, when you see a SP log like this, you have to understand each little variations, okay, to describe the shales. So tiny shale or evaporite structures can be occurred. So you have to describe all these chains, okay. A geologist, this is the job of a geologist, but as a petroleum engineer, also you have to understand this one, and you understand that if something couldn't catch, you have to describe that one. You have to identify that it's a shale structure, tiny shale structure in here, right? Okay. Because you know, sometimes what happens, for example, sandstone B and sandstone D, okay? Let's say sandstone B and sandstone D. So these are, because of the shale, tiny shale structure, this can be shown as different pay zones, but these are not different pay zones actually, because somewhere in here, for example, somewhere, for example, 100 meters above your well, okay, they may be combined. This shale structure finished and they combine, so they have connection. Okay, your sandstone B and sandstone D has a connection in far away. Okay, so they will affect each other maybe. Okay, so you have to understand this. So you have to clarify what's happening around your wellbore. This is very important. Okay. Okay. So 3, the imagine-related anomalies. Imagine-related anomalies. So for example, if the mud filtrate and the formation water have significantly different salinities, okay, and therefore the different densities, the gravity-induced fluid migration can cause spontaneous potential anomalies in highly permeable formations. Okay. So invasion is a very shallow near the lower boundary of each permeable interval actually, and deeper near and upper boundaries. Okay, so it has to be described as well. So the SP curve is rounded at the upper boundary because of the deep invasion, and it may have a sawtooth profile at the tip. Okay, impervious actually shale strikes in which the SP deflection exceed the SSP above the shale strike, a reading greater than the SSP is caused by the accumulation of filtrate below the shale strike. Okay. Encircling the hole is a horizontal disc of shale sandwiched between salt water and fresher. Okay, salt water and some fresher water. Actually, fresher mud filtrate that acts like a battery cell. So EMF of this cell is superimposed on the normal SSP, producing the sawtooth profile. We call it sawtooth profile. Okay. Okay. So another one is noisy SP logs. Noisy SP logs, especially in the offshore logging environment. Okay. It is notorious for its ample to study the source of electrical noise, such as wave motion, cathodic protection systems, rig welding, onboard generators, and leak power sources. So, proximity to lower lines and pumping wells may have similar effects on the SP curve, but the effects can usually be minimized by carefully choosing the ground electrode location. Okay. These are, from this point, we will go more into the technical details. So I will stop the SP in here, okay? So I will pass to the caliper log. We came to the last slides, okay? So I came to the caliper log. So we said that caliper log we were using to borehole measurement, right? You can see, for example, here, you can see the different types of caliper logs, okay? 3-arm, for example, dual axis, 2-arm, 4 to 6-arm, okay? And single axis also is valid. This is an old one actually. Single axis is valid. There's a single axis, 2 axis, dual axis, sorry, 3-arm and 4 to 6-arm versions you can see. For example, here, as you can see, this is the real borehole is like this, something like this, okay? Not a circle one, a real borehole like this. So when it is coming to the up, all these parts, are contacting with your borehole, okay? And then it's opening and closing and measures, making the measurement, okay? So that's what I can say. We already mentioned all of these. So the most important applications of caliper logs, we can say, borehole geometry and stability and breakouts. The indication of the permeable zones, mud cake, okay, indication. The thickness of this mud cake, it gives an idea. The indication of fractured zones, it gives an idea. The borehole volume for cementation operations, I already mentioned this one. It gives an idea regarding on these. Okay. So the commoner uses of caliper logs are contributory information of lithological assessment, indicator of good permeability and porosity zones, reservoir due to the development of mud cake in association with the gamma ray log, always. Association is very important. So calculation of mud cake thickness, measurement of borehole volume, and the measurement of required cement volume. Okay. So there are some factors which influence the response of the caliper actually. For example, your hole diameter, okay, on gauge, your hole diameter if it is a well consolidated formations and non-permeable formations, okay, the possible lithologies that you will get the massive sandstones, calcareous shales, igneous rocks, and metamorphic rocks. If your hole diameter is larger than the bit size, formation soluble in drilling mud, it's sourced by the formation soluble in drilling mud, and it can source the formations weak and caving. Okay. Salt formations drilled with fresh water, consolidated sands, gravels, and brittle shales. If it is smaller than the bit size, formations swell and flow into the borehole, and the development of mud cake, porous and permeable formations. So possible lithologies are swelling shales, porous, permeable sandstones. Okay, so these are the caliper response influences can be given. Okay. So I wanted to put this one as well as a part of your future notes. It will be beneficial when you involve to operation in the future. You will understand the reason of that. So thank you very much for your attendance. This is the end of week 3. This is the end of week 3. So if you have any questions, I will be glad to answer your questions actually.
Yes, teacher.
Yes. Please.
Teacher, which chapter in mid-exam?
Again?
Which chapter will be in mid-exam?
Which chapter?
Yes, in mid-exam, teacher.
In the exam, you mean? I couldn't get your voice.
Yeah,
Midterm.
yes,
in
midterm.
the midterm.
In the midterm. Okay, which chapter? So in the midterm, we were planning to make it in the 8th week. Okay, so the results of the first 7th week. So I was planning to add first 7 week, but the midterm will be in 17th of April. So it will be in 7th week. So because of that, we will not involve the 7th week topic. Okay. So first 6 weeks will be included as the topics of this. All right, your midterm.
Yes.
First 6 weeks.
Thank you.
Okay. So I hope that it clarified a little bit in your minds, because I am sure that you were hearing these log types, spontaneous potential, gamma ray, caliper, and the other ones. Hope that it clarified a little bit. So don't worry about your midterms. Just concentrate on what we are giving physically in here, what we are trying to giving in physically. All right. As I told you, these are the basics, but it has to be learned. When you go, for example, some of them had done maybe your internships, or some of you will do some more. So this will be crucial when you are doing your internship, starting from your internship, and in your future career as well. Okay. So because of that, I am trying to give this as combining it with my field experience as well. Okay. Industrial experience, because it's very important. I don't want to just theoretical information. I want to give it by combining with the real cases. Okay, from my mind, I am giving you the things that I live, as I am trying to give it, because physically I want to make it live in your minds. Okay, and that's what I aim to do, because it will be very useful in your future career. I am sure about that. All right. So this is the end of the week 3. Any questions? I